Okay, welcome back to microeconomics. So starting from now, we will go to the second topic of the course, choice and demand. And especially for this week, we will look at the utility functions, its concept and some examples. And then we see the formalization of utility maximization under budget constraint, which we have seen a little bit of it last week, but we will go deeper in details and also how to solve them, the properties of it, and so. Let's go. In everyday life nowadays, we all consumer. So we ultimately will have to deal with a decision-making problem, which is quite famous in microeconomics, which is to choose the best set of goods that you can afford. Now, this problem has two parts. The first is the best set, the best according to preferences or utility, what you like, what you prefer. The second part is afford. So afford because we face some sort of budget constraint. We don't have unlimited amount of resources or money to spend on the goods that we would like to consume. So let's talk about these two parts. Now, utility, the first part is about preference. So utility is an indicator for ranking the bundles of goods. And its absolute size or value is not important. Why? Let's see by the example below. So assume we have three sets of goods, A, B, C. A person rank these baskets according to his or her preference or favorite. So set A is the most favorite of this person, has 3 units of utility in total. Then the set B is the second favorite. So it brings her or him 2 units of utility. And then set C is the least favorite because he or she only earns 1 unit of utility with this set. Now come a second person. So this person has for each basket 3 times as much utility as the first person. So his or her utility is 3 times the utility of the first person. However, the ranking stays the same. For this person, A is also the most favorite and C the least favorite. We have another third person. Now the utility level that this person obtains from the three sets always negative. So it's always 4 units less than the first person. However, again, the ranking remains the same. Would you be possible to say which person enjoy a certain set the most? No, right? Because simply utility is something you can't not compare across individuals. It's subjective, right? So only the ranking matters here. Let's say, for example, I like wine better than beer. I earn 10 units of utility with wine and only 5 with beer. And you also like wine better than beer, but you earn 15 units of utility for wine and 10 units of utility for beer. Does that mean I like wine much more than you like it? No, because we use different scaling system. And that's why it's not to compare across individuals. However, to avoid the confusion later, it matters when we compare the different choices that each person has. For example, like here, the value that each basket A, B, C brings to each person, for example, the first person would matter for his ranking, right? So it matters when you talk about one single individual, but not between person and person. Back to here, the two utility function U2 and U3 can be called a monotone transformation of the utility function of the first person, the U1. So you might remember last week we talked about monotonic transformation already. So these cases include there. Now, and the ranking again stay unchanged. So the order preserved after the transformation. When you have something like that, these three utilities functions called equivalent ordinal utility functions, which means it represents equal ordinal preferences, equal ranking. So let's look at some typical examples of references. The first case is the perfect substitute. What does that mean? So imagine our utility depends on the consumption of both blue and red pencil. Perfect substitute means the indifferent curve, the curve which shows the same utility level given different combination of goods that we consume, right? This curve will be aligned in this case. So let's say we obtain this level of utility by consuming 5 blue and 5 red pencils. That is total 10 pencils, right? And then now if we only have 2 blue and 8 red pencils, we on the same indifferent curve. So it doesn't matter how many colors you have as long as you have the same number of pencils in the end. Your utilities stay the same. Therefore, the line will be 45 degree downward sloping. Why downward sloping? Because of the trade-off, right? You have decreasing number of blue and increasing number of red. Because of that, the slope is negative. We'll talk more later. Before we go to the next case, there's something also helpful to realize at this stage. So like before, let's say we on this utility level, the indifferent curves, which is U equal to 10 pencil in total, doesn't matter which color. So the utility function in this case can be written as U1 equal X1 plus X2, total number of pencils. So what happens now if, for example, we double the number of pencils? It will become U2 equal to X1 plus 2X2. So that is we move to a higher level of utility, right? With U2 equal to 20 now. And that means a parallel shift of the indifferent curve to the right-hand side. And similarly, if now let's say we, instead of increasing, we decreasing, so U3 equal to 5, then U3 of X1, X2 will equal to 0.5 X1 plus 0.5 X2. So if we decrease it, that means the indifferent curve will shift inward to the right, to the left-hand side, sorry. Next case, complements, perfect complements. So you have to consume something together with something else. You can't consume them separately or use them separately. One example in this case, the left shoes and the right shoes. You have to have them all together. Other examples are car and its wheels, or in my case, coffee and milk. So how does the indifferent curve look like in this case? It will be an L shape indifferent curve. Why? Let's think about it for a moment. And while we're looking at the form of the utility functions, in this case, the form will be u equal to mean of x1 and x2, whichever is smaller. So now let's think about it. Assume you have only one right shoe, right? So you have one right shoes here. And you have two left shoes. The utility that you would get from this quantity of shoes is from only one pair, right? Because one extra left shoes wouldn't help. So similarly, doesn't matter how many more left shoes you have along this line, you will always end up on this indifferent curve. You will not be able to move up to the next utility level unless now you have a second right shoes. So in this case, you will move to the next level of utility from two pairs of shoes. The other way works also for the right shoes. Let's say now you have three right shoes, but only two left shoes. You will also end up on this same utility level of two pairs of shoes. And similar if you go for 4, 5, 6 right shoes. But if you only have two left shoes, then that means two pair of shoes, no more. So that's why that functional forms has the mean over there, mean of x1 and x2, whichever is smaller. All right. And similar in the case of cars and wheels, we will add another parameter for the wheels. So that is mean of 0.25 wheels and one car. All right. Those are two extreme cases. Now let's look at something more normal, a normal preference. What does that mean now? The normal preference will be characterized by a curve, not straight line anymore. One example is u equal to x1 times x2. We have seen last week before. And then again, here is worth stressing again, anything to the left of the indifferent curve will means we wash off. So we get lower level of utility on the left-hand side of the indifferent curve. On the other hand, if we move to the right-hand side of the curve, that means we move to higher level utility. So we better off. Now there's two important axioms of normal preference. The first one is called monotonicity. More is always better. So that implies that the slope of the indifferent curve is negative. Why is that the case? I show you with drawing in a minute. Now let's move on to the second axiom. So the second one basically said that if you have some combination of average between the two goods, you always end up better than with extreme case when you have too many of one good but too less of the other. So that implies a convex indifferent curves. We'll see. So to see clearer the implication of the two axioms on the curve, the indifferent curve, let's do a bit drawing. So here, the first thing is why monotonicity implies negative slope. So I have put some graphs here in advance. Here we have a downward sloping or a negative slope indifferent curve on the left-hand side. And let's say we have, let's say, change it to red. Let's say we have a point A with x1a and x2a on the curve. And yeah, this is some sort of combination of x1 and x2 at point A. Let's put it here. Now, if you keep the quantity of x1 the same, but you increase your consumption of x2, let's say, so it should be here. Yeah, x2, let's call it point B. Yeah. So this point B is actually on the right hand side of the indifferent curve, which we have said anything on the right hand side of the curve is better, right? So we have higher utility at this point compared to on a curve. So more is better. That's the first scenario. The second scenario, if you keep x2 constant now, but you increase the consumption of x1 only to point x2, x1, let's say C. So this point C, at this point C is still on the right hand side of the indifferent curve. So it's better than on the curve itself. Now what happens if we increase both? So if we increase to x2b, and then x1c. So let's call this point D. It's even further to the right, right? So even better, so to say. So because of that, negative slope implies that more is always better than less. Why it does it not the case with the positive slope? Let's see on the graph on the right hand side. So now again we have, let's say at this point is A, so x1a and x2a. Sorry, typo here, x1a and x2a. So there's a point A, right? Now, if you keep x1 at the same level, but you increase x2 only, let's say, to this level, x to b. So now point B is actually on the left-hand side of the curve. Anything on the left-hand side is worse. So we will be worse off and up at B than at A, right? However, if we now keep x2 constant, but we increase x1 to x1c. Let's say this is point C. At this point, it's actually on the right-hand side of the curve. So it's better. So you can see that the patterns is not really consistent with the case of the positive slope in different curve. That's why the monotonicity axiom implies the negative slope. Okay, let's move to the second axiom, where we said averages are better than extremes. And why does it have to be the convex indifferent curve? So last week we talked briefly about it. If you remember, concave function implies that if you have 2 points, A and B, then you draw a line to connect these 2 points, which I have already done here. Then the line will be below the curve. And the other way around for the convex function. So the graph here on the left-hand side. If you connect 2 points on this indifferent curve, then the line will be above. No, it will be above the indifferent curve itself. So now what does it have to do with average and extreme? So any point on this line connecting A and B represent some sort of average combination of both, and it's less extreme than at A, where you have a lot of x2 but only a few of x1, right? And on the opposite, at B you have a lot of x1 but only a few of x2. So those 2 points are quite extreme. On the other hand, if let's say if you have here C, a point C, you have something average of the two, a more combination, right? And this point, the C, lies on the right-hand side of the curve, so it's better. And that works for the convex function. Let's see on the concave function. The same thing here. If you have an average combination of the two, let's say C, x2C, x1C, you see that because the whole line lies, below the curve, and that means to the left of the curve. So anything to the left is worse off. So for that reason, average is not better than extreme. In A, where you have again a lot of x2, you're better. Or at B, where you have a lot of x1. Sorry. Yeah, that's true. So here it should be x1b. All right. So for that reason, the implication is the indifferent curves must be convex.